Saxon Algebra 2, Lesson 56, Geometry. We're going to talk about angles in circles. Actually, we will be exploring these in more complicated types of problems in the future. So this isn't a bad lesson to just give us a little vocabulary and then show us some relatively simple calculations. So it's a fairly straightforward lesson, and I hope you won't be too upset. You won't be upset. You love every lesson because math is fun. Ready? Here's a circle. There's the center of the circle. Here is an angle. It looks like a Pac-Man, doesn't it? It looks like a Pac-Man taking a bite. I think it does. This is called the central angle. It's a central angle because it's an angle that comes from the center of the triangle. Oh my gosh, what a great inspired name. This section right here, now pretend I'm writing right on the line of the circle. I'm going out from it a little bit so that you can see what I'm doing. This is called the intercepted arc. If you imagine this as a Pac-Man's mouth biting the circle, the intercepted arc is the size of the bite he takes. Notice that the measures of these are exactly the same. The measure of a central angle equals the measure of the intercepted arc. That's super handy and good to know, right? Let's contrast that with what we call an inscribed angle. An inscribed angle does not start at the middle. The inscribed angle starts all the way over on the far side. This, my friends, is no Pac-Man. This is a Teenage Mutant Ninja Turtle on profile. Can you see it? His eye is here, his mouth is here, here's the little ties hanging down. I'm not gonna clutter up my picture. But this is a Teenage Mutant Ninja Turtle. He has different rules. He is an inscribed angle, as I said. We would call it that. I'm not gonna put in a number there yet, but there he is. This is his intercepted arc. Now, he's not biting it like a Pac-Man angle, but it's his field of vision. I don't know. It's the width of his bandana, right? Or whatever you call it, his ninja mask. We're gonna call that 70 degrees. That is his intercepted arc. He's not biting it, but it's the same situation, right? Now, here's the thing. When we had a central angle, the measure of the angle was the same as the intercepted arc. When we have a inscribed angle, it doesn't match like that. This is not 70 degrees. What this is 35 degrees. The angle is half the size of the arc, or if you want to say it the other way, the arc is twice as big as the angle. Ah, interesting, right? I think we've talked about this before. So this is a different kind of relationship than this, right? Okay, let me remind you of a few other vocabulary words. We'll draw 3 circles across the bottom. Ready? 1, 2, 3. This is a secant. A secant is a line that passes through the circle. It doesn't have to be in the middle. It just passes through at some angle. It hits both sides, right? This is a chord. And in a chord, I'm going to draw it at roughly the same angle, but it doesn't have to be. A chord is just the segment of the line. It doesn't extend outside. Now, this has always bothered me. Ready? I'm going to unload this drama onto you. This, to me, looks like the circle in an acoustic guitar, and this looks like the string that passes over it, right? It goes up to the fret and then down to whatever it's called, the part of the guitar where it is anchored at the bottom. This reminds me of a guitar string. It seems like that should have the musical word to describe it. I would like this to be called a chord and this to be called a secant. But you know what? I don't get my wish. This one, the guitarish looking one, has the non-musical name, and this stubby little thing is called a chord. The injustices of the world. I don't know what to say. If you take a secant and you move it all the way to the edge of the circle so that it's not passing through two sides, but it's just brushing up against the edge, it's hard to draw perfectly. Ooh, that's not perfect. Pretend it touched right there, right? This is called a tangent. Different than the tangent we use in trig. Same word, but different idea. And the cool thing about tangents is if you draw a line from the point of tangent, mine doesn't look right at all. If you draw a line from the point of tangent to the center of the circle, that will be a right angle. It does not look like it on mine, does it? But trust me, it's true. This forms a right angle with the radius. Okay? Words for you to know. Okay, let's get into some problems. Ready? There are 4 different types of circles we're going to look at in this. So you might want to start on a new page. And let's just draw the 4 circles. Give yourself some space to write. Okay. In the first circle, we're going to show 2 lines that intersect inside the circle. They're not necessarily going through the center. These are not diameters. They're just random lines that intersect inside the circle. And they are chords. I'm not going to write the circle. I'm just going to write inside. Now, we know these are vertical angles, right? So we know they have to be the same size. And in order to calculate them, we look at their intercepted arc. These are not central angles. These are not inscribed angles. They are something different, okay? That was just kind of general review. In order to find out how big these X angles are, we can take the 2 intercepted arcs and find the average of them. So these X angles are 60 degrees. Add that, you get 120, divide it by 2, that's 60. Okay? So this is one style of lines of different variety, in this case they're chords, that we're looking at. In the next example, we're going to look at 2 secants that cross outside the circle, right? So it's 2 secants that intersect outside the circle. Okay, we want to find this angle here. We're calling that X. Now, in order to find the size of that angle, we need to know the 2 intercepted arcs. All right, let me draw the X out here and make it pointing in because that's too crowded. We want to know the size of this angle. In order to find that, we need to know this intercepted arc and this little one in here. We're using the same numbers, but don't worry, it's going to be different. to find this value for x, we take the bigger number and wait for it. We subtract the smaller number and divide by 2. So this x angle out here, this is just a little bitty 20-degree angle. Okay? This angle right here. Make sense? I know that got a little messy. Sorry. I'll try to be neater on the next one. The third one is an example where we are combining a tangent and a secant. Okay, so let me try and draw. Here comes the tangent. That is a pretty good looking tangent for a hand drawing. And here comes the secant. Okay, so this one is tangent and secant intersect outside the circle. Okay? I'm underlining those words because they're important. So this is our tangent, this is our secant. Again, we're trying to find this angle. That's our x. And again, we look to our 2 intercepted arcs. We need to know what these are. This is where the tangent touches, that little line. All right, and we are told that this is 120 degrees and this is 60 degrees. So to find the value of x, we take the 120 and we subtract the 60 and then we divide it by 2. 120 minus 60 equals 60. 60 divided by 2 equals 30 degrees. And here comes the last one, which is going to be 2 tangents. I'm going to move this up a little bit. There's one tangent. I have to turn my book, but I'll put it back in just a second. 2 tangents. Pretend they're perfect. They're not terrible. Okay? So here we have 2 tangents that intersect outside. All right? Again, we're trying to find the measure of this angle. I'll color it in so you can see it better. We're calling that x degrees, right? That's what we found in all of these, is the measure of that angle. That's x. And again, we're looking for the intercepted arcs. Now, what's interesting about these tangents, when we have 2 tangents, is that between the outer intercepted arc and the intercepted arc, it's the whole circle, right? Because the tangents just touch at a certain point. So we're getting the whole circle in the end. That's an interesting thing to keep in mind. 2 tangents intercept the whole circle. Okay, but we need the calculation. We find out that the outside bit is 260 and the inside bit is 100. So to find this angle, we will take 260, subtract the 100, divide it by 2, you guessed it. This is 160 divided by 2 is 80 degrees. All right? So, looked at what we did. We have 4 different scenarios that involve chords and secants and tangents. 1 intersects inside the circle. 3 intersect outside the circle. Notice that when we intersected inside the circle, we added, I'm going to use a different color. For emphasis, when we intersected inside the circle, we added. When we intersect outside the circle, we subtracted every time. All right? That's your takeaway. When lines intersect inside the circle, you add them an average. When lines intersect outside the circle, you subtract larger from smaller and then average the difference. Okay, we divided by 2 in every single case. What changes is whether you add or subtract, all right? These problems most students find kind of fun, kind of safe. Look here in the book, and you'll see, oh look, here's intersecting inside, intersecting outside, outside, and outside. All right? So you can just use the rules that we developed, and those calculations should be fairly painless. And guess what? That is the end. Oh, I just want to explain to you what John's doing here. He has another section called proofs. What he's doing is he is proving to you why, these are John's 4 circles. They're similar to the ones we drew. He's proving to you why that's true. Here's the thing. I think that's very noble of him and very caring of him to want to make sure that he proves his mathematical chops to us and doesn't just tell us stuff without backing it up. But I'm going to go out on a limb and say, I don't think you care that much. I think you trust John. I think you trust me to tell you the truth. And you've got your hands full just memorizing what's going on here and making sense of that. You don't really need a thesis on why that's true. For now, you're willing to just believe that it's true. That's what I'm going to go with. If you wake up in the middle of the night in a cold sweat because you just aren't sure if you should believe me that this is true, then by all means, turn to page 242 and read this, and it will prove to you why this is the facts. If you can live your life without doing that, trust me that next year in advanced mathematics, we're going to get into proofs a little bit. John teaches them much better in that book than he does in this book. These are clunky and hard for you to follow. But next year in the green book, we will tackle proofs, and they're a dream. They're much easier to deal with. So for now, I'm going to skip over that and ask you to just believe me that all of this is true. And again, if you wake up with sweaty nightmares and a racing heart because you just don't feel good about it, there it is, page 242. All right? Guess what? That's all. Goodbye.